So this is example 1 of projectile motion. We've got a cannonball that's launched from a platform 8 meters high at a velocity of 23 meters per second and an angle of 60 degrees above the horizontal. The question goes, how far away will the ball land? So it's kind of planned out here. You can see a screenshot of the simulator, which is how I'll base all these examples on the simulator. So the cannon is being launched from this point down here. The cannon is inside the ball is inside the cannon. You can't really see the ball at the moment, but the ball is inside. It's in here. We know that it's going to initially have an angle here. It's going to have a velocity of 23 meters per second and an angle of 60 degrees above the horizontal. And there's the horizontal line. That's the line that I'm talking about, the horizontal line. Very, very important for you to realize that every instant, it'll only be 60 degrees for that first moment. And after that, the angle is constantly going to change because it's going to launch into a parabolic trajectory. Okay, trajectory being the flight path. Okay, the word for the flight path. So it's going to look kind of like this. So it's going to launch here. It's going to have a horizontal component, and then it's going to have a vertical component of that velocity at every time. By the time it gets to the very, very top, there'll be no more vertical component of that velocity. So there'll only be a horizontal component, and then it'll be on its way back down, where it'll pick up a vertical component again, but it'll be going in the downward direction. So the first thing to do with a question like this is to is to take what you're given. You're given the velocity, which is 23 meters per second. You're going to break that down into the velocity in the x direction and in the y direction. So if you can't remember how to do this, please go back on vectors, which is 1.3. So you know that your initial velocity is 23 meters here, 23 meters per second. That means that Vx is going to be V cos theta and Vy is going to be V sine theta. Subbing in here, we're going to take the initial velocity here, so we'll use U instead of V. So the initial velocity in the x direction is going to be the initial velocity times cosine of the angle. The initial velocity in the y direction is going to be that initial velocity 23 meters per second times the sine of the angle. Plugging in the numbers, that gives you 11.5 meters per second in the x direction and 19.9 or almost 20 meters per second in the y direction. And if you think about it, that means that most of the velocity is in the upward direction at that instant. And that should make sense because the angle is greater than 45 degrees. Okay, if it was at 45 degrees, then you would expect that you'd have as much in the x direction as you do in the y direction. But here you're above, you have 60-degree angle, so you've got more of that velocity in the y direction than you do in the x direction. Okay, now it's important now at this point, we've started with our initial velocities, and it's very, very important for us to set out our frame of reference. Okay, I really probably should have done that from the very start. And just like we'd said before, we're going to say anything that points up is going to be positive, anything that points to the right is going to be positive, whatever points down will be negative, and whatever points to the left is also going to be negative. Okay, so just looking at the data we've got here, that distance there, 15, means nothing because that's just the default setting on the simulator. But you know that you're going to have an x component and a y component, so your ux is going to be here, and that's clearly positive, and your uy is going to be here, and that's clearly positive as well, because both of those are either pointing, well, this one's pointing to the right, this one's pointing up. Those are both positive. Then you've got a height here. Now, if you think about it, basically what's going to happen is the cannonball is going to be launched up here. It's going to come at some point down here somewhere. I'm not 100% sure where it's going to land, but it could be over here maybe somewhere. Okay, That's our job, is to figure that out. So that means that the change in position for the ball is actually going to be SY, the displacement for the ball, is going to be negative 8 meters. Okay? Please, please, please do not forget that needs to be a negative 8 meters. So the next thing to do is to split your data up. So I always make a table, X data and Y data. The X data has only got the stuff that's concerned with the X direction. The Y data is going to be a bit more complicated. That will have stuff only concerned with the Y direction. Please bear in mind, acceleration is only in the Y direction, because we discount all air resistance. So therefore, there is zero acceleration in the X direction. Zero acceleration. A equals 0 here. Okay. AX is negative G, or negative 9.81 meters per second squared. So that means if it's if you've got zero acceleration, that means you're going at a constant velocity. So basically, you're just using distance, speed, and time. Or velocity equals displacement in the X direction divided by the time. List all of your knowns here, whether you know them or not. Your initial velocity in the X direction, your displacement is unknown, that's what you're after. Your time for the X is going to be the same as the time for Y, which is, we just call that T, we drop the notation. And then you do the same thing in the Y direction. Please remember, acceleration only affects the Y direction. You've got your initial velocity in the Y direction, your final velocity here, and I have a little asterisk here. We are going to solve for the final velocity first, no matter what, because it will simplify the calculation big time. Then your displacement in the Y direction, well, we know that that's negative 8 meters because it has come down by 8 meters. Right. Next thing to do is to solve for the Y direction, the final velocity in the Y direction. And here's where I'll use this formula here. The final velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. Bearing in mind that these two guys are both negative. So when you sub in your numbers here, you should have negative 8 and a negative 9.8. And they should that should work out to be plus. Okay. You evaluate that and you wind up with 552, and I always do it in 2 stages here. I then take the square root, and it's at that point that you have to remember the final velocity in the Y direction must be negative. Your calculator will give you back a positive value, but you have to be smarter than your calculator, and you have to realize that on its way down, it's going to have a negative velocity. So that means that you have to assign it a negative because that's what fits with our frame of reference. Okay, once you've got that done, the next step is to go for time. Solve for time, because remember, time in the Y direction is going to be the exact same as time in the X direction. So I'm just going to use the equation final velocity equals initial velocity plus acceleration times the time, solving for the time, and that gives me subbing in the numbers, I've got 4.429 seconds there or thereabouts. So that gives me the total time. Now all I have to do is take that time and sub it back in for my values in the X direction. Yeah. So finally, step 3, which I've done here. Yep. I'm going to take the displacement in the X direction. It's going to be the velocity in the X direction, the initial velocity in the X direction, and it should be the same velocity throughout because it's a constant velocity. I know I'm labouring that point, but it is worth mentioning and re-mentioning. So that's got you 11.5 meters per second times your time to give you 50.9 meters, or sorry, 50.93, or approximately 50.9 meters. And then all we did was we tested. So I just moved my little cursor to the 50.9, hit launch, and hey presto, it lands there. So that's what your job is to do, is to set some initial conditions. You set an angle, you set a height, You use the mathematics to predict exactly where it's going to land, and then fire and see whether or not you got it right. Okay, best of luck with that. Sorry, the simulator is on the very top of the page here. Okay, best of luck with that, guys.